In this lecture, I'm going to introduce and summarize the basic structure and properties of crystalline solids. So I'm going to do this by assembling a massive table that summarizes the properties of the four major different types of crystalline solids. Um, what you ought to do right now is pause the video and reproduce this table in your notebook. We are going to have the major heading, the types of the crystals. The four different types are the ionic solids, the molecular solids, the network crystals or covalent network crystals. Sometimes these are called network solids, as well as the metallic crystals. And then we're going to kind of organize the information according to the particles that make up the different solids, the attractive forces that hold the particles together, their relative melting points, whether they conduct electricity, some of their physical properties. Are they hard or soft? Are they brittle? Can you mold them? And then a couple of examples of each type of crystal. So pause the video, get this table set up, and then we can resume our discussion. So we are talking about different types of crystalline solids here. And what governs the structure and properties of solids is twofold, really. You have what type of particles make up the solid and the type of attractive forces that hold those particles together. These two features will determine what kind of solid you're dealing with. So some of these solids you've seen before. Ionic solids, of course, are made up of cations and anions. So cations and anions are oppositely charged ions that we know are held together by electrostatic attraction. And the electrostatic attraction here is a very strong type of interaction called an ionic bond. Okay, so ionic bonds are what hold oppositely charged ions together. These are very, very strong interactions. And because ionic bonds are so strong, ionic solids tend to be high melting. Okay, it takes quite high temperatures to disrupt those bonds and liquefy the solid. Their conductivity is kind of interesting. The conductivity is low for the solids themselves, but if you melt them or dissolve them, the conductivity becomes very high. So I'm going to put high when melted or high when dissolved. Okay, I'm running out of room in my table here. But what happens is, okay, so when you have ionic solids in their crystalline solid structure, those ions are pretty much locked in place in the crystal lattice, so there's not a lot of opportunity for the charge to move. But if you get very high temperatures and you melt those solids, the charges start moving around and you get some conductivity. If you dissolve the solids in water, for instance, then once again, you have charges moving around and the resulting solution will be highly conductive. So what are some of the physical properties? Well, ionic solids, you can think about salts. These are hard, very hard solids. They are brittle. Okay, they are definitely not soft. And of course, the examples are pretty much any salt that you can think of. So salts, for example, we have, well, of course, the classic one, sodium chloride, but it could be any salt. Potassium carbonate, calcium carbonate, potassium bromide. Why not potassium carbonate, calcium bromide? Any salt that you can think of. Lithium fluoride, magnesium chloride would be an example of an ionic solid. All you need to have are oppositely charged ions that are held together. All right, moving on to the next category, we have the molecular solids. Now, molecular solids are made up of molecules. So when you have molecules that are held together, the forces that are holding them together are intermolecular forces, London forces, or dipole-dipole forces, or hydrogen bonds. So you have individual molecules that are held together by intermolecular forces. Now, compared with actual bonds, intermolecular forces are not as strong. So these molecular solids are low melting, especially compared with ionic solids and the rest of the solids in this table. Similarly, because they're molecules, we don't have charged particles. So the conductivity is low. And once again, because intermolecular forces are not quite as strong as, say, ionic bonds, physically they tend to be soft. So molecular solids are soft, low melting, non-conductive solids. What are some examples? Think about molecules. Ice. Okay, water is a molecule. Solid water is ice. Ice is a relatively low melting, soft solid. And yes, it is soft on a relative scale compared with something like salt, and especially compared with the next category, the network crystals. Let's take the molecule carbon dioxide. If you get cold enough temperatures, you get dry ice, solid carbon dioxide. This would be an example of a molecular solid. Any molecule, so sugars, any type of sugar, sucrose, glucose, would be a soft, low melting solid. Okay. So any kind of molecule, if you get cold enough, you can solidify it, and these would be relatively low melting and soft solids and with the molecules held together by intermolecular forces. All right, carrying on our discussion, the third category I have here are the covalent network crystals. Sometimes they're just called network crystals by themselves without the covalent word, but I like covalent because it helps you remember what they are. Now, covalent network crystals are kind of special. The particles that make them up are just atoms, and they are nonmetal atoms. That's a good way to differentiate them from metallic crystals. So nonmetal atoms. And those nonmetal atoms are kind of uniquely held together in a long, huge covalent network. So the nonmetal atoms are held together in a long network of covalent bonds. So in this case, it's kind of hard seeing the formulas to distinguish them from molecules. But what you have here, you don't have individual molecules. You have this vast continuous network and no individual molecules. And what this does is it gives rise to very high melting points because you have this super, super network that is difficult to disrupt. However, conductivity is low for network crystals because you have nonmetal atoms. You don't have ions, you don't have moving charges. For conductivity, you need to have moving charges. So for network crystals, conductivity is low. However, because of that huge extended network of covalent bonds, they are very, very hard. And as an example, diamond is a great example. Diamond is just pure carbon. Of course, it has impurities, but in its essential state, it's just pure carbon. And those carbon atoms are covalently bonded to each other in this huge extended network. And of course, we know that diamond is very hard. Another example would be sand or quartz. Quartz has the formula SiO2. But here in quartz, you don't have any individual SiO2 molecules. You have the Si and O atoms all bonded together in this huge extended covalent network. Okay, and this gives rise to very hard solids. The final category that we're going to talk about are the metallic crystals. The particles here are metal atoms. So, looking at the periodic table, the metals are on the left, the nonmetals are on the right. This is one way you can distinguish these things. Um, Really, it's electrostatics also holding those metals together. You kind of have this sea of electrons, um, mobile electrons, and the mobile electrons in metallic crystals make them really conductive. Okay, so you generally have high conductivity. Um, the melting points for metals are variable. You can get fairly low melting metals and also high melting metals. I'm just going to put high here because it would be higher than the molecular solids in general, but not as high as the network crystals. And it's highly variable. Now, metals have the really unique property. Some are soft, some are harder, but metals have the unique properties of ductility and malleability. Ductile and malleable. And what this means is that they can be molded. Ductile means they can be molded into a wire. Malleable means that they're able to be formed into different shapes. And that's unique among these solids. So that's the kind of most outstanding physical property of the metallic crystals. Now, um, the example, well, any metallic element is going to be an example of metallic crystals. So whenever you see a metal on its own, iron, copper, silver, gold, sodium, any metallic element all on its own in the zero valence state is going to be able to kind of symbolize a metallic crystal. All right. Out of these lists that I've just written down, copper, of course, is an excellent conductor. Silver is also a good conductor. So these vary in their conductivity. They vary a bit in their physical properties and melting points, but um, you can spot them by finding any metallic element kind of all by itself.